Okay, in this video, we are going to finish up the derivation of the radiation you get from a oscillating electric dipole. So where we ended up in the last video was we now have a solution for the electric field, which we solved from the potentials. We first solved the potentials, now we're solving for the electric field. Now let's take a look at the magnetic field. So the magnetic field, B, is going to be the curl of the vector potential. And so I can write that out now as in spherical coordinates 1 over r d dr r a theta minus dA r d theta, and all of that in the phi direction. So it turns out from the equation for the potential A right here, so it's only in the z direction, and it only has, which really means that it only has components in r and theta. And so, okay, so this is the only term in the cross product that survives. Okay, so if we now want to work that out, we would get minus mu naught p0 omega over 4 pi r omega over c sine theta cosine omega times the time part plus sine theta over r sine omega t minus r over c, and all of that is in the phi direction. Okay, so I kind of already worked out all those derivatives ahead of time. Yeah, feel free to go ahead and do that on your own, just to prove to yourself that this is the solution to both of those derivatives. Okay, but what we can do is now we can look at, say, approximation number 3, which says that the distance at which I'm measuring the magnetic field is much, much bigger than the wavelength of the radiation. Or another way of saying that is 1 over r is much, much less than omega over c. So it's much, much less than 1 over the wavelength. Okay, so that helps because I can essentially just ignore this component right here, because that means that they both have a sinusoid, they both have a sine theta in their terms, and they both have a trig function, cosine or sine, with respect to the time. But what I'm saying is that this term here, omega over c, is much bigger than this term 1 over r. So I can neglect that second term, so I can make that approximation. And when I do, what I get is a magnetic field, which is minus mu 0 p0 omega squared over 4 pi times c sine theta over r times cosine omega t minus r over c, all of that in the phi direction. Okay, so what we can do is we can compare that to what we got for the electric field up here. So why don't I write that down just for comparison? And what you see is you get minus omega naught p naught. So I'm sorry, mu 0 p0 omega squared 4 pi sine theta over r cosine omega t minus r over c in the theta direction. So what you can see right away is that those two terms are basically the same, except for a factor of 1 over c. So one thing we can notice is that if we just look at their magnitudes, the magnitude of the electric field divided by the magnetic field is c. So you recover this relationship that E and B basically give you the same behavior within a factor of the speed of light. The other thing you can notice is that the direction of the vectors is orthogonal, or essentially that one is in the phi direction, one is in the theta direction. So we can make the claim that the electric field and the magnetic field are perpendicular to each other, which is what we've come to expect in our study of electromagnetic radiation or electromagnetic waves. The third thing, which is a little bit more subtle, is that both of them are in phase with each other. So you notice that in theta, they both have a sine theta over r term, which I can label right here. And they both have this cosine term. There's no phase angle in the cosine term, so they're completely in phase with each other. So we basically have these electromagnetic waves, which are doubly transverse, and they're in phase with each other. And the overall amplitude of the waves of the fields is only a factor of the speed of light difference. Okay, so now let's take a look at the power, and to look at the power, we have to then consider the Poynting vector, which we said is 1 over mu naught E crossed into B. And since everything is essentially the same between them, what we have is 1 over mu naught P naught omega squared over 4 pi sine theta over r cosine omega t minus r over c squared. Now there's the 1 over c factor between them, and the cross product is only now between their vector directions. So it's theta crossed phi. Okay. So what does that give us? That gives us a Poynting vector, which is mu 0 over c p omega squared 4 pi sine theta over r cosine squared, all of that in the r direction. So now the electric field is pointing in the theta direction, magnetic field is pointing in the phi direction, and the power is now radiating outward in the r direction. So its power is now radiating is radially. It's moving radially. If we average over time, then what we get is the only thing that is time dependent is the cosine. So we would be integrating over the cosine squared dt, and the integral of the cosine squared is 1/2. So the average of the Poynting vector is mu 0 p0 squared omega to the 4th over 32 pi squared times c sine squared theta over r squared in the r direction. So that is our average So what does that mean? Well, there's a sign in there. So that means if theta is equal to 0 or theta is equal to 180 degrees, then our average is 0. And in the end, what you get is then this sine squared over r squared shape, which looks like essentially the power is radiating outward in this toroidal shape to it. So that would be the power which is now expanding outward like a donut, where there's no power on the axes pointing up or down. So in this direction here, instead the power is now radiating outward, like I said, in this toroidal shape. And so essentially what you have is this radiation field which is now expanding, not as a sphere, but as a donut, and expanding out into space. The magnetic fields are now pointing in the phi direction. The electric fields are now pointing in the theta direction, right here. Okay. So in the end, I guess what we can write out is if we want to find now the average power, then the average power is going to be the integral over, integrating over the area of this pointing vector, which in the end gives me mu 0 p0 squared omega to the 4th over 32 pi squared c integrating sine squared theta over r squared sine theta d theta d phi, because it's a surface area. So the r squareds cancel, and we get a 2 pi for the integrating over phi, and then you have to integrate sine cubed, and what you get in the end is mu 0 p0 squared omega to the 4th over 12 pi c. So this is now the average power integrating over the entire area. So in the end, what you see is that the frequency dependence, to the power at least, goes as the frequency to the 4th power. So that means large frequencies are going to dominate and lower frequencies are not. And so we can kind of make a statement that what we should see from dipoles is higher frequency radiation, something in the blues and the purples, and less in the reds and the oranges. Which, you know, I guess then you can make the blanket statement that, well, our atmosphere is made of dipoles. The atmosphere is predominantly nitrogen and oxygen. And so now these dipoles, as they radiate, well, let me not draw it that way. As these dipoles oscillate up and down, back and forth, then the light that they're going to emit is going to be in the blues. So what we'll see is mostly blues and purples, which matches. The sky is blue.